Okay, so today's lecture is going to be a continuation of the last lecture, which discussed this notion of boundary value problems. Solving problems, specifically structural analysis problems, posed in the form of some governing differential equation that must be satisfied with the solution of this equation being some corresponding function that we're looking for, which characterizes the displaced state of this resulting structure. So in general, just to kind of recap what we covered from last time, if you didn't have a chance to go and watch the last lecture, I welcome you to go review that and just kind of catch up on some of these topics. But in brief, what you would have missed is this development of posing specific problems, as you might encounter in the structural analysis setting, which sought to find what is the resulting displacement of this structure, and not just the displacement at any discrete point, but the displacement at any and all points along the length of this, let's say, one-dimensional structure, subjected to some externally applied loads, maybe a distributed load applied over the length, maybe like an end load applied at one of these external boundaries of this domain, let's say, and also subject to additional boundary conditions on maybe the displacement field itself corresponding to any constrained supports. So in that setting, it becomes a direct constraint on what the value of the displacement field is at this particular location, let's say x equals 0. Okay, so we posed these general boundary value problems as being basically a statement of saying, I'm looking for a function that lies in maybe the set of all possible continuous functions, which is kind of a requirement of compatibility. I have to have a continuous displacement field in order to ensure that the structure doesn't split apart as it starts to deform under these applied loads. So it has to be a continuous function at a minimum, and it has to satisfy this governing differential equation at every single point within this structure, such that it satisfies this statement of equilibrium in that kind of pointwise sense. And it also has to satisfy these boundary conditions, either constraints directly on the displacement at prescribed support locations or constraints imposed on what's the externally applied force at maybe this end of the membrane. So that's what a boundary value problem is. It's a statement of, we're going to solve this structural analysis problem for this kind of unknown displacement function or this displacement field. All right, well, that's very nice. You can go about solving these boundary value problems analytically as posed in this particular format. And we actually presented a particular example of that in the last lecture. If you want to kind of have the step-by-step walkthrough of that, you're more than welcome to go back and review. But otherwise, really the problem with these boundary value problems as we posed them has to do with this question of, well, how do we actually solve these boundary value problems in general? If I have maybe a very general applied load or applied distributed load P as a function of X, really the question becomes, how do I come up with a solution to this particular boundary value problem given this distributed load? How do I solve for what the resulting displacement field is, itself kind of this function of position? Now, you can go about solving these particular boundary value problems rather easily in a one-dimensional setting and assuming things like linear elastic material behavior and other kinds of things that make solving these problems quite tractable. But there are a few challenges that we encounter if we try to apply that same methodology to other scenarios in which maybe the choice for how we're representing this distributed load might become rather complicated. And it's not entirely clear how we might go about solving for what the displacement field of the structure should be such that it satisfies equilibrium in this pointwise sense everywhere. So that becomes kind of a complication. Other issues with that kind of approach that we walked through in the previous lecture are that it requires computing these integrals, basically. Given the particular form for this distributed load P, in order to solve for the displacement field, analytically anyways, we have to integrate whatever this function is with respect to X, not once, but twice. And if this function becomes particularly nasty, it's not exactly clear how to carry out these analytical integrals, at least not in an automated way. What we'd really like is to find some kind of solution procedure that is generalizable and which we can kind of implement in this automated fashion and hand off to a computer so that the computer can do all the work for us. But in the way that we formatted this problem, it's not necessarily amenable to having a computer do all of those steps. We kind of have to work out all those integrals in an analytical sense ourselves, with pen and paper. Now, another issue that you can have is that there's even more complicated situations that arise if we have not just this one-dimensional structure. What if we had a two-dimensional structure or a three-dimensional structure? Those are kind of the types of problems that we're working towards in this class. And in general, these analytical procedures doing this double integration method works in one dimension, but it doesn't work in general if we want to solve 2D or 3D types of problems. So even worse. And then if we introduce further complications like nonlinear material behavior, or maybe the structures, applied loading changes as a function of how the structure is deforming. So there's some kind of large deformation effects that we have to consider that introduces further geometric nonlinearity. And under these, additional constraints and considerations, solving boundary value problems in this general format really becomes almost impossible. So at least in the way that we've posed these problems, in this particular statement as shown on the previous slide, solving this problem is rather trivial, but as we introduce all these other complexities, it becomes really insufficient to use these classical methods to analytically solve these boundary value problems. We need something else. We need a different approach. And that's precisely the subject of what we'll get into today. Alternative formulations of nonetheless the same boundary value problem, but just kind of stated in a slightly different format. But really, I want to highlight what is the major difficulty in solving these boundary value problems as we have currently posed them. Really, what I've reinforced and hopefully drilled into your mind at this point is that when we're trying to solve these boundary value problems, our constraints, the functions, or kind of like the equations that we have to satisfy, are really not just a single equation or a discrete set of equations, but it's really this statement, a governing differential equation, that has to be satisfied in a pointwise sense at every location x within this particular structure or within this particular member of interest, which basically means that we have as many of these equations as we have points or discrete locations along the length of the structure. However, because we're dealing with a continuum mechanics perspective of things, there's really an infinite number of these points at which I have to satisfy this constraint or this equilibrium condition. Or in other words, I basically have to satisfy this constraint an infinite number of times, or an infinite number of points. So that's really the challenge here. We have not just one equation. This is an infinite number of equations that have to be satisfied at an infinite number of these points everywhere inside of the structure. So that really throws a wrench into the works of how do we actually solve these problems if we're solving a set of equations for posed at a discrete or an infinite number of points in the structure, and what we are trying to actually solve for, this displacement field, it too can be characterized as basically a function where what we want to know is what is the value of this function at an infinite number of these points. So if you like, you can interpret that to mean that the way that we're representing this particular solution really requires us to introduce as many unknown values of the displacement field as I have discrete points. So at this point, I might have an unknown value of the displacement field there. At this point, I have an unknown value of displacement that I have to solve for. So really, there's an infinite number of equations that we have to solve and an infinite number of points entailing an infinite number of solution unknowns. And there's a proportional number of these unknowns to the number of constraint equations that we have to satisfy. So at least we have as many equations as we have unknowns, but there's an infinite number of both of those things. That's the problem. That's the problem with solving these boundary value problems, at least in the way that we posed them. So what's the solution here? How do we work around this problem? We don't want to solve an infinite number of equations for an infinite number of unknowns. That's intractable. We don't have that kind of time. So what's the solution? Well, you probably already had an idea of where we're going with this. We've already alluded to this at the start of the class when we were solving not for an infinite number of unknowns with an infinite number of equations, but rather with a finite number of unknowns, solving a finite number of equations. And that's really the approach that we take in trying to break this problem down. We say we're not going to satisfy equilibrium everywhere. We're not going to satisfy it perfectly at every single point along the length. And also, we're not going to solve for what the displacement field is everywhere. We're just going to pick a few discrete values of displacements, maybe at certain particular locations that we're going to actually solve for. So that's the approach. We're going to make the problem simpler by making it smaller. Discretize the problem, choose a finite number of locations at which we might want to enforce equilibrium. And there's a couple different ways that you could do this. Probably, the simplest way that you might think to do this is to just say, well, okay, let's take you at your word and, let's try this. Let's just pick a discrete number of locations along the length of the structure, kind of like we would do in a finite element method, where we say, let's just choose a discrete number of these points or nodes along the structure, at which we'll choose to define these discrete values of the displacement field at those specific locations. And in addition to that, we'll also suppose that we're not necessarily enforcing this equilibrium condition everywhere at every single point along the length. I'll choose to enforce it also at some discrete number of points. And just to kind of keep things consistent, maybe I'll choose to satisfy it also at these same locations. So I'll pick some discrete number of points, x1 through xn, some discrete number of collection of points as shown here, and I'll come up with a discrete set of unknowns representing the displacement at each one of these points, and a discrete number of equations corresponding to this statement of equilibrium just evaluated at each one of these different points. That's kind of at least a simplistic approach to try to solve this problem, right? And it seems like it should work. And in fact, this particular type of method is called a collocation scheme, or a collocation method, which basically says we're going to try to solve this differential equation, not everywhere, just at these kind of discrete collocation points at which we're also representing discrete values of the solution unknowns. Now, the problem with this is that we might be specific about saying what's the value of the displacement at each one of these discrete locations, but we've said nothing about what's the value of the displacement field or this displacement function at any location in between these discrete values. To reconstruct what the solution values should be in these regions where we haven't really explicitly stated what the value of the displacement field is there, we kind of have to guess or kind of extrapolate, or rather interpolate, the specific values of the displacement field in between those different regions. So if we have no way of directly saying what the displacement field is, we kind of have to just come up with some way of representing these intermediate values in terms of the discrete values. And typically, interpolation procedures are the way that you do that. Representing this kind of interpolating function that passes through these discrete values, but kind of reconstructs intermediate values. All right. Now, collocation methods are fairly simple, fairly straightforward to construct. It just leverages this statement of equilibrium in its differential form as we previously posed it. But there's a downside to trying to solve problems using this collocation scheme. And really, there's two problems. The first problem is, take a look at this particular term involving the nabla operator with a slight abuse of notation. Just kind of replace the nabla operator, this upside down triangle, with a derivative with respect to x. So really, the nabla operator is nothing more than derivative with respect to x of this kind of interior quantity involving E, A, and the derivative of u with respect to x. Now, here's a problem. What if I had, what if I had maybe some member that didn't necessarily have uniform material properties? And specifically, suppose I had two members connected end to end, such that, the material in one end of this member has some larger value of the Young's modulus compared to this kind of other member that might be connected to it. Maybe this kind of component is made of steel, and maybe this one is made of some kind of polymer-based material or something like that. If I chose to represent the variation in material properties E as a function of position, in other words, I might have something that looks like this. Yeah, there we go. So suppose I had this. Suppose I chose to represent this particular variation in material properties such that I have two distinct values of the Young's modulus, which changes value if I'm kind of to the left end of this structure or less than this kind of x naught value that lies at the interface between these two junctions. And it jumps in value kind of in this instantaneous way. Now, this particular representation of this jump in material properties is characteristic of a function representing how the Young's modulus should behave as a function of x, such that maybe it has E1 here, and then at x0, it jumps up. So it's a discontinuous function. Now, the problem here is that what happens if I were to plug this discontinuous function representing that jump in material properties into this expression? And what would happen if I chose to take this partial derivative with respect to x of this whole expression? Would I have a well-defined expression for the derivative of that whole thing if e is a discontinuous function? Is the derivative of this function even well-defined at this particular point where I have this discontinuity? No, I see a lot of shaking heads, kind of some concerned faces, and that's the appropriate response. This is really one of the problems when you have these governing differential equations expressed like this. It basically means that if I have any kind of discontinuity, it could also be a discontinuity in the member cross-section size. So two distinct members of differing cross-sections joining at one end could mean that if there's a discontinuity in that representation, then I can't take the derivative there. The derivative is not well defined at that location. Similarly, even if the strain field is discontinuous at this location also, that introduces a complication. So really, if we're trying to solve these problems, we kind of have to insist that this interior term, which is basically just representative of the internal force in this member, we would have to ensure that at least this function is differentiable at any points where we're trying to evaluate this derivative with respect to x. So as currently posed, if we don't have a well-defined derivative, especially at the collocation points where we're trying to evaluate this function, then we can get ourselves into trouble. And that's really a huge problem. It's a huge limitation of trying to solve these problems posed in this particular format using this expression for equilibrium, entailing a partial derivative of how the internal force field varies as a function of x. So there's restrictions on the types of functions and solutions that we can actually get out of solving this particular set of equations. So that's a huge limitation. We need some extra smoothness requirements imposed, which may not necessarily be representative of real-world physical scenarios, where you may in fact have these kind of discontinuities or jumps in material behavior. The other issue is that if we're picking a discrete number of these collocation points or discrete points where we're going to choose to satisfy equilibrium, one of the issues with that is that, well, what kind of biases our choice of particular points in assessing whether or not equilibrium is satisfied at some discrete number of unknown locations? Is it possible that if we chose only a discrete number of unknown points, let's say x1 through xn, at which we're going to exactly enforce these equilibrium constraints, is it possible that at maybe some intermediate points between, let's say, xn and xn minus 1, perhaps, maybe there's a point in there where we really egregiously violate this particular condition there? In other words, we're not really equally weighting all these different points. We're just picking a discrete number of points at which we're saying, let's satisfy equilibrium here, but you could have gross violations of equilibrium at these intermediate points. So that's kind of another issue with these collocation methods. Really, this is the one that makes it almost impossible to solve practical engineering problems, the first one of these problems. But they're both equally concerning. So we need to find a way around this issue. We need to find a way around both of these problems. And the way that we do this is actually to try to come up with a different way of formulating these kinds of problems. And to distinguish this new way that we're going to attack this problem, we really have to distinguish the old way that we were doing things. And in particular, the way that we pose these boundary value problems is in a format called the strong formulation of the boundary value problem. which states that we have to satisfy this governing differential equation as posed and seen here in this kind of pointwise sense. And this particular format for solving the strong formulation of a boundary value problem involves all of these extra problems that I've said. It kind of imposes some artificial requirements on the smoothness of the internal force field, and it limits the types of solutions that we can actually admit as solutions to this particular boundary value problem. So we have to find a workaround to that. And we have to find, well, you'll kind of see where I'm going with this. Rather than a strong formulation of this particular boundary value problem, we have to find a somehow weakened formulation or a weak formulation of this same boundary value problem that nonetheless gives us an equivalent statement of the same problem, but which gives us a little bit more of a relaxed requirement on perhaps how the internal force varies internal to this member and makes it a little bit more amenable to solving these boundary value problems in an approximate sense using methods that we'll discuss in later lectures. All right, so given this strong formulation, is there some way that we can manipulate it into an equivalent but weakened formulation of equilibrium? That's the goal. All right, so to do this, we start with our governing differential equation expressing equilibrium in this pointwise sense. And we're actually kind of going to go backwards from the way that we originally derived these equations. We started in deriving these equations by posing equilibrium not in this kind of pointwise sense, but we actually started with describing equilibrium in kind of like an integral sense. We were integrating this whole interior integrand term over the domain of some structure of interest. And that's how we actually originally posed statements of equilibrium on, let's say, some one-dimensional bar. So in other words, if I took this pointwise statement of equilibrium, a statement of equilibrium that has to be satisfied at every point, let's say from 0 to L inside of some uniaxial member, equally, I could just say, take this expression, integrate it over the full length of this member from 0 to L, and what I'll get is actually a statement of equilibrium that describes the equilibrium not at a single point, but actually over the whole bar. So in some sense, that's equivalent to saying, let's take the sum of forces acting on a bar of finite length L. So this statement, as shown in this box, is really equivalent to trying to consider, let's say, a bar of length L to which we might be applying some external loads. And there might be loads applied at these ends, maybe some distributed load applied along the length, and the sum of all these forces applied to this bar of length L can be equivalently represented basically like this. So that's one way that we can take this pointwise statement of equilibrium and work backwards to effectively posing equilibrium over discrete kind of subsections of this bar that might be integrated over, I don't know, some subchunk of this or over the whole darn thing as shown here. Now, if we wanted to do some kind of statement of equilibrium, let's say over a finite slice that nonetheless had, let's say, some discrete length, delta x or something like that, what we could do is we could take this same integral, but then just plug in, let's say, some kind of special function that basically has zero value here, but then just is equal to 1 over this sub-chunk. So that's another way that we could identify, let's say, posing equilibrium on some small subset or sub-chunk. We could take some kind of heaviside step function or something like that, plug it into this integral, and basically make it equivalent to saying, let's just integrate over this small chunk to pose equilibrium on that chunk. Alternatively, we could be funny. We could say, well, why have a step function even? You know, why does it have to be 0, 0, and then just equal to 1 over this interior region in order to pose equilibrium of this chunk? What if I had a more general function that maybe it was mostly 0 here, and then it kind of like ramped up, and then kind of smoothly transitioned from a 0 value to maybe a positive value or something like that? And in fact, doing that gives us a way of expressing equilibrium in something of an integral average and weighted sense. So in other words, I could come up with some function which I'll call V, sometimes called a test function. But in other words, it's also kind of like a weighting function. It could be one of these Heaviside step type functions that assumes like a discrete value, such that our interpretation is that we're effectively stating equilibrium over some kind of finite chunk over which that particular function value is equal to 1, elsewhere equal to 0. Or we could describe it as a nice, smooth, continuous function that kind of like samples or tests the statement of equilibrium in this kind of like smoothed out way to identify the collection of points over which that function might be equal to something other than 0. So in other words, I can come up with this equivalent statement of equilibrium in this weighted integral average sense using some generically defined test function. And as of yet, I haven't really been specific. It could be this Heaviside function. It could be, some random, smooth function, and it could identify maybe any small window along the length of this member. We haven't really been specific. But regardless, if we know that in a pointwise sense, this internal expression always has to be equal to 0 everywhere if equilibrium is to be satisfied, then trivially, it doesn't really matter what this function is, because if I have the integral of something that has to be 0 everywhere times this arbitrarily chosen test function, then this statement always has to be equal to 0, regardless of how I've chosen that arbitrarily selected test function. So it's equivalent to say that this integral expression multiplying this thing, which should always be 0, any function, any arbitrarily chosen test function, that resulting expression for this integral expression of equilibrium has to be equal to 0. Now, what we can do with this is we can say, well, let's just choose some random test function. It might look like some kind of nice Gaussian curve. It could be some, it doesn't really matter what it is. It could be any function sampling, different values of this kind of statement of equilibrium in a pointwise sense at any kind of arbitrary, subset of this member. So the main conclusion here is that ultimately we could choose any such test function. We could plug it into this weighted integral average statement of equilibrium, and it should always be equal to 0, regardless of how we've chosen that particular test function. So that's kind of the main thing. We've transformed this statement of pointwise satisfaction of equilibrium into an equivalent integral average statement of equilibrium that has to be satisfied for any particular choice of this test function. And another way to interpret this is that we could take, let's say, any arbitrary collection of these material points, and the sum of their kind of forces applied at each one of these points, kind of sampled from a different subset or collection of those points, always has to be equal to 0. All right, so what can we do with this? Well, to really see the value of this, we have to actually transform this preceding representation of this integral statement of equilibrium weighted by this test function. We need to make some mathematical manipulations to this expression in order to get something useful out of it. So bear with me. We'll go through a few steps, but really it's not so much more complicated than some of the tools we've already developed thus far. All right, so given this expression, and just making some substitutions to make it a little bit easier to read, the expression that involved the partial derivative with respect to this term, that term, in fact, was just the internal force within this particular member. So I can just plug in that particular value of F. Now, given this particular statement, I can actually use the product rule of differentiation to recognize that if I have the partial derivative with respect to X of, let's say, the product of two functions, let's say F and V, now it turns out by the product rule of differentiation, this derivative of the product of these two functions is really nothing more than V times the derivative of F plus F times the derivative of V, which basically means that this term involving the derivative of F times V can be manipulated such that I can replace it by the derivative of F times V minus F times the derivative of V. It seems like a little bit of a, well, what did we get out of that, really? Well, you'll see in a moment. But given that we've manipulated things in this way, we can actually recognize that this particular term, the derivative of F times V, can actually be transformed using the fundamental theorem of calculus, kind of like we applied previously when we were deriving the original pointwise statements of equilibrium. We can take the integral of this derivative of F times V And notice that the integral of the derivative of this thing gives us back just simply the thing, the product of this kind of these two functions, f and v, just evaluated at the endpoints of this particular interval from 0 to L. So it turns out this is just equal to f at L times v at L minus f at 0 times v at 0. Small manipulation, but you'll notice the important thing that we've gotten out of this kind of two-step transformation is that the problem that I pointed out earlier in having this expression involve a derivative of the internal force field, which required that the internal force field was differentiable, I've done a few manipulations and voila, look, now I don't actually have any derivatives with respect to f, which means that if I wanted to evaluate this expression, which is entirely equivalent to this expression, I can do so without actually having to take any derivatives of f, meaning I don't necessarily require that the internal force field has to be a nice, smooth, and continuous function that has well-defined derivatives. That's an important realization. It basically means we've worked around that first problem that we had pointed out when we were opposing equilibrium in the previous strong formulation of the boundary value problem. All right, now that we have this, we actually have to impose a few restrictions on the way that we're selecting this arbitrarily specified test function. Now, it'll become clear exactly why we're enforcing these constraints, but suffice it to say, let's imagine that we chose this test function, and more specifically, let's kind of put some constraints. Let's impose some constraints that say that this test function has to be itself a continuous function, similar in some respects to the way that we've imposed this same requirement on the displacement field. And also, let's require that this test function also has to satisfy so-called homogeneous boundary conditions. In other words, at any location where we were originally constraining the displacement field directly, at these same locations, we have to directly constrain the value of this test function such that it's equal to 0 at those constrained locations. All right, so that's kind of just a minor thing to bear in mind as we move forward, but just a minor restriction on how we define these otherwise arbitrarily chosen test functions. All right, resuming our mathematical manipulations. Coming back to this expression that we derived on the preceding slide, and remembering that we've worked around this issue. We don't necessarily have this derivative with respect to f we have to deal with anymore. We can take a few additional steps. We can actually impose some of these boundary conditions that we put in, including the one that we just introduced, which says that at any location where we're constraining the value of the displacement field, at that same location, we're going to insist that the value of whatever this test function is has to be equal to 0 there. So in that sense, we notice that this term, v at x equals 0 is just equal to 0, so we can get rid of this thing. And we can also recognize that F, the internal force in this member, evaluated at L according to our force boundary conditions, basically say that if there's an external force applied at x equals L, then we can just plug that directly into this expression and replace F at L with just this externally applied boundary condition on the force, F bar. So we make those substitutions. We plug back in our expression for the internal force as depending on E times A times the strain field or the derivative of the displacement field to get this expression. And then lastly, we can kind of just move things around to different sides of this equation to finally arrive at our statement of equilibrium, a weighted integral average statement of equilibrium that is nonetheless equivalent to the thing that we had previously, just after a few minor manipulations. And again, I want to point out some interesting features of this resulting expression that we've obtained. Again, we don't have any derivatives with respect to the displacement field or any of the material properties of this member, so those things could be potentially discontinuous. The strain field could be discontinuous. The variation in material properties or cross-sectional properties, those could be discontinuous. Any of that is allowed, and we can still carry out this integral, which is nice. We have, let's say, we've actually included whatever external force boundary conditions directly inside of this expression. We don't necessarily have to enforce any of these extra boundary conditions by setting some unknown constants of integration that we would determine in the process that we would normally adopt when we were solving the strong formulation of this same problem. So we've actually incorporated directly any of our force boundary conditions directly in this statement of equilibrium. And it turns out that this particular formulation of equilibrium in this integral weighted sense has a particular name, as I alluded to previously. It is, in fact, the weak formulation of equilibrium, or the weak formulation of the corresponding boundary value problem. It is, nonetheless, totally equivalent to the strong formulation of equilibrium as previously developed. The important thing to note here is that instead of saying that we're searching for some displacement field that had to be continuous and which satisfied equilibrium in a pointwise sense, now we've manipulated into the following expression: find the displacement field which doesn't satisfy equilibrium in a pointwise sense, but rather satisfies equilibrium in this weighted integral average sense. But it has to satisfy this expression for any possible choice of arbitrarily selected test function v. So it basically says I could choose any of these arbitrarily selected weighting functions or test functions v, plug it into this whole expression, carry out the integrals, and whatever I get, this expression should still be valid. All right, it's nonetheless equivalent. Now, you'll notice that the particular choices of these displacement fields and this test function, actually, I'm saying that they belong to specialized sets of functions, which I'm respectively denoting u and v with this kind of uppercase, calligraphic font to denote that I'm referring to particular sets of functions to which the displacement field must belong and a set of functions to which this arbitrary set of test functions must belong. Both of them consist of functions that themselves must be, at a minimum, continuous functions. So they have to belong to C0, the set of all possible continuous functions, at a minimum. Some other things, this set of functions also requires that maybe the solution for the displacement field has to also satisfy whatever displacement boundary conditions I've imposed on that displacement field. So built into this statement of this particular set of functions, it comprises the set of all functions that are C0, and in fact also have to be in this set of functions H1, which, if you remember way back when we were talking about sets and spaces, function spaces in particular, I defined this set of H1 functions as the particular set of functions that are L2 integrable, or basically square integrable, whose first partial derivatives with respect to the function itself squared, integrated over some kind of finite interval of interest, that the resulting integral to be a finite value. Now, you can imagine why that's important in this context. Imagine I had some function u, and indeed also some function v, and suppose I had them defined such that the integral of this expression of the partial derivative of u integrated against some other function, partial derivative of v, what would happen if I had some functions that cause this whole integral expression to blow up and become, let's say, some infinite value or a non-well-defined value? Clearly, in that case, I would get some kind of nonsensical result here. So at a minimum, I require that this particular function u and also, in fact, v, that they have to have their first derivatives be at a minimum integrable in this kind of L2 integration sense. All right, so that if you want to kind of get some of the details of that, you can go back to the earlier set of slides when we were discussing sets and spaces to reconcile exactly what this means in this context. But it basically just imposes the constraint that for any particular choice of u and v, I just need to ensure that this integral doesn't blow up. It doesn't become an infinite value. So it's a pretty relaxed constraint on what these two different expressions for u and v need to be. They have to be continuous. They have to be defined such that this integral expression doesn't blow up, and they also have to satisfy these additional boundary conditions that we've imposed on them. So the displacement field at this particular location has to be consistent with whatever external displacement boundary condition we put there. And similarly, the value of the test function at this same location itself has to be equal to 0 at that same displacement boundary condition. Okay, this statement of weak equilibrium in this kind of weighted integral average sense enables a whole bunch of other stuff that we'll discuss probably in the subsequent lectures. But it also kind of begs the question, what are really the main advantages here? We've kind of like talked about, well, we've worked around the issue that we had previously where we no longer require that these terms need to necessarily be smooth or differentiable. So we've worked around that particular constraint. But there's some other interesting things that are worth observing. We can find solutions which maybe have a discontinuous strain field, which satisfy this particular statement of equilibrium, but which don't necessarily satisfy that pointwise statement of equilibrium as posed through the strong formulation of the boundary value problem. So in fact, we've actually expanded the possible set of functions and possible solutions to these boundary value problems through this statement of the weak formulation of equilibrium. And really, weak, the terminology weak, comes from this fact that we're weakening the requirements on what conditions this particular displacement field has to satisfy. It doesn't have to be differentiable. And that weakened condition on differentiability is really where the weak in weak formulation comes from. So just to kind of reconcile exactly why it's called what it's called. All right. Now, all of this is probably a little bit abstract, and you're probably thinking, what the heck is the point of this whole test function? Does it even have a physical interpretation? And how does this all connect back to concepts from structural analysis that you might be previously familiar with? Is there some way of understanding these concepts in a way that doesn't involve treating things as these like weighted integral averages over some intermediate domain? And in fact, there is kind of an interesting analog and interpretation of what exactly this test function is that probably is more familiar to you. And specifically, it comes back to this concept of virtual work. Who here is familiar with the principle of virtual work, as you might have encountered it in, let's say, an undergraduate structural analysis class? Raise of hands if you've heard of principle of virtual work. All right, a fair number, okay. So if you remember the principle of virtual work, the idea was this. Given some kind of structure, which might be subjected to some set of external forces and which might have some internal forces defined inside of it, the principle of virtual work stated that if I have some definition for all these forces applied to this structure, I can imagine what is the virtual work done by those forces moving through a particular virtual displacement. So if I have, let's say, a block that has some external force F bar applied to it, and I imagine maybe it displaces by some amount V, a virtual displacement, if you will. It doesn't actually displace by this amount. We just suppose that maybe if it moved in this direction, we could then quantify what is the work that would be done on this whole system, given this external applied force, if it were to move through this kind of virtual displacement. And we can quantify what that virtual displacement is just by saying the product of force times virtual displacement gives us virtual work. Now, the principle of virtual work established a relationship between the external virtual work done on this system, let's say any external forces applied to this block to move it some finite distance. It established a balance between external virtual work done on the system and internal virtual work done in, let's say, stretching the material locally. And that could be measured, let's say, by considering how much does some block of material stretch if it were to be subjected to some virtual strain field. Or in other words, if I had this virtual displacement field and I took its derivative, I could take that definition to mean or interpret it as something like a virtual displacement, an imaginary stretching that might happen internal to this material. And given the definition of this virtual strain field, I could come up with a definition of virtual internal work that would be done stretching this block of material and including whatever internal forces might already be acting on this block of material. Now, the principle of virtual work effectively establishes this balance, that whatever external virtual work would be done on this system, moving through this particular virtual displacement field, must be balanced by any internal virtual work that would be done in moving through this kind of internal set of forces stretched through this virtual strain field. So in effect, this statement of balance between external virtual work and internal virtual work for any possible choice of these kind of virtual displacement fields leading to external virtual displacements applied to the structure or internal virtual strains throughout the whole structure, that this statement really has to be true for any possible virtual displacement field. Doesn't really matter how you define it. In fact, the previous statement that we derived, this statement of equilibrium in this weighted integral average sense, is nothing more than the statement of virtual work applied in this particular setting, where on the left-hand side, we've kind of collected all the terms that involve the virtual work done by any externally applied loads. Let's say F bar applied to the end of this member, and P, the distributed load acting along the length. The total virtual work from these sources has to be balanced by whatever internal virtual work is done moving through the virtual strain field. Okay, and as long as those two things are equal, we effectively have a statement of equilibrium. Okay, so that's kind of an interesting connection. If you're familiar with some of those principles or kind of recall some of those details from your undergraduate structural analysis class, I'd invite you to go back and maybe revisit some of those topics and reconcile how they kind of relate to some of the subjects in this class. All right, now it actually stands to reason that if we're actually considering this, let's say, test function as in fact a virtual displacement field, it now makes a little bit more sense why we're imposing some of these constraints or requirements on how these test functions can be defined. If you remember, I said previously that these test functions or virtual displacement functions, if you want to interpret them that way, that they had to be continuous functions and they had to satisfy these kind of extra homogeneous essential boundary conditions. Anywhere that we were prescribing the displacement, let's say a constrained support, we also insisted that our virtual displacement field at that same point had to be equal to 0. And the way to interpret these requirements is to suppose that if we have a displacement field, even if it is virtual, it should still at least be representative of some possible virtual displacement that the structure might undergo while still satisfying the requirements of compatibility and whatever other displacement boundary conditions we put on the structure. So, under those conditions, if it is to be truly like a displacement field, which itself has to be continuous, then also this virtual displacement field should be necessarily a continuous function. So clearly, those two requirements saying that both the true displacement field and this virtual displacement field, whatever it is, they have to be continuous functions. And also, if we took some arbitrarily chosen virtual displacement field, and if we were to add this arbitrarily chosen virtual displacement field to the original kind of chosen displacement field itself, we should get back a displacement field that still satisfies this boundary condition. And if we were to do that, if you take this function and add it to any possible virtual displacement function that looks kind of like this, and if you also impose this additional requirement that the virtual displacement function has to be equal to 0, wherever we're assigning these kind of discrete constraints on the displacement field, in doing so, we guarantee that summing these two things together ensures that we still satisfy whatever boundary condition we're putting on the displacement field. So that's kind of another way that we can rationalize why, if we're imposing this constraint on this virtual displacement field, why we actually have to do this. It's to ensure that if we add these two things together, we still get back satisfaction of the original kind of constraint, the support constraint. All right, that's all we have time for today. If you have questions, feel free to ask. I think we have like a couple minutes. If not, we can kind of adjourn and you can visit me in office hours and we can continue there. Any questions before we end it? All right. I'll see you next time. Probably next week, most likely.